let's just get into it. I'm going to talk about the Taylor series. So it turns out that this comes up quite a bit in physics. So let's just look at what it is and how you do it. So let's imagine that I have some function. This is the x-axis, and this is f of x. And I know what the form of it is, but let's just say it goes something like this. Like that. There's my function. Okay. So sometimes we want to represent that function as a polynomial. So suppose I want to find the value of this point and close to that point for some function. This comes up a lot if I want to do something like f of x plus epsilon, some small amount, and I want to see how this varies around that point. But I don't want to actually use the function. I want to use a polynomial. So this is what the Taylor series is taking a function and representing it as a polynomial. And polynomials are much easier to deal with. So let's just say I have some other function, I'll call it g of x. And let's say it's a polynomial, so it has some constant term, I'll call that a0, has a1 times x plus a2 times x squared plus a3 times, that's a 3, times x cubed and so forth. So I have that polynomial. I don't know what these coefficients a0, a1, a2, a3 are, but I want it to match up with the function at x equals 0. I'm doing this as x equals 0 first. Okay, so technically it's not a Taylor series, but that's fine. Don't worry about it. Who cares what it's called, right? No one cares. So if I have this function and I want it to match f of x at the point x equals 0, so I'm at x equals 0. Well, then the first thing I want to do is I want the function g of x, so I want g of 0 to be equal to f of 0, right? They have to have the same value. Well, that's pretty easy. So g of 0, if I put in 0 for x's, only one term survives, because that's 0, 0, 0, so the only term I have left is a0. So a0 is going to be equal to f0. That's okay. Next, I want also the slope of my function, my polynomial function, to be equal to the slope of f at that point. So I want g prime of x at x equals 0 to be equal to f prime of x at x equals 0. And you don't normally put the derivatives that way. I didn't want to put 0 in there. I want you to know I'm still taking a derivative. I guess I should have written this as I should have had this as g prime of 0 equals f prime of 0. And so just to be clear, f prime of x is going to be the derivative of f with respect to x. So I'm going to take the derivative of that. And if remember, I have to know what this function is. I can't do a Taylor series for something I don't know what the function is. Now I can take the derivative of g of x also. So I can get g prime of x. G prime of x is going to be equal to the derivative of a0, which is 0. The derivative of a1x is just going to be a1. So it's a1 plus, now I have a power series here, so I have to bring the 2 down. I get 2a2 times x plus 3a3 times x squared. And I could have more terms, but I just picked 3 for right now, and I think that'll be good enough. Now if I do g prime of 0, I put in 0 for x, and I get a1 plus 0 because I'm putting in x's there. So that has to be equal to f prime at 0. Where I said that has to be true. So I know what f1 is. Okay, let's do it again. I also want the curvature to be the same, right? The curvature is the second derivative. So I want the second derivative to match up too. So I can do the same thing. Let's take the second derivative, g double prime of x. If I take the second derivative, I can take the first derivative of g prime of x. So I get a1 times 0, and then I get 2a2, and then I get plus 2 times 3 times a3 times x. If I put in g double prime of 0, I get 2a2. And then this is 0, right? Because I have x is equal to 0. And that has to be equal to f double prime of 0. So that's good right there. Now I need to do one more time. Let's take the third derivative of g prime. I'm going to do it right up here. Triple prime of x is going to be equal to, well, now that term goes away. I only have this term. I get equal to 2 times 3 times A3, and then G triple prime of 0 is going to be F triple prime of 0, and that's going to be equal to 2. Yeah, so this A2, actually I should write this. A2 is F double prime 0 over 2. And this is going to be 2 times 3 times A3. So A3 is going to be equal to F triple prime of 0 over 2 times 3. And maybe we can see a pattern here. Okay, let's write down the pattern. So let's write down this one. A0 equals F0 over 1. And then I can write A1 as F prime of 0 over 1. And then I can write A2 as F double prime 0 over 2 times 1. 2 times 1 is 2. Yeah, and you think, what? Why would you do that? Okay, well, maybe you can see. A3 is going to be F triple prime of 0 over 3 times 2 times 1. And now we can get a general expression for any A, right? Because this is 0 factorial, this is 1 factorial, this is 2 factorial, and 3 factorial. So in general, AN is going to be equal to F, they write it this way, Fn 0 over n factorial. So remember factorial, let's see, 5 factorial is going to be 5 times 4 times 3 times 2 times 1. 0 factorial is 1. I don't know why that's true. That's just the case. So that's my general function for an. That's the nth derivative at 0. And then I could also say f of x is equal to the sum from n equals 0 to infinity an x to the n. That's my polynomial right there. Okay, but now what if I don't want to do this at x equals 0? Well, let's have a function right here. Let's say I'm going to kind of draw that same function. Make it look the same. But I want to find it at x0. I want to expand the function about that point. Well, I could say, what if I make a coordinate transformation? What if I say, shift this over such that u equals x minus x0. If I do that in the u coordinate right here, it looks like that, I am back at the origin. Right, so I just cheated. So instead of writing x, all I need to do is put x0. So this gives me the following definition for the Taylor series. F of x is going to be equal to the sum n equals 0 to infinity, an x minus x0 to the n, where an is the nth derivative of f evaluated at x0, over n factorial. Okay, let's do this for an example. Let's do this for a couple examples that are very common, and I'm going to show you how it matches up. Let's do a simple one. Let's do f of x equals e to the x. I mean, you really can't get easier than that, right? Because we can take the derivatives of that at x equals 0. Okay, so the first thing I want to do is to say f of 0 equals what? Because I need to find a0, a1, a2, a3. We'll go that far. So a0 is just going to be f0. If I put in x is equal to 0, I get 1. So a0 is 1. F prime of x is going to be e to the x. This is actually really boring, you can tell. So if I evaluate this at x equals 0, I get 1. And because remember, a1 is equal to f prime of at 0 divided by 1 factorial. Now this one I have to divide by 2 factorial. So I'm going to get the same derivative. I'm going to take the same derivative again. So I get 1, but now I need to divide by 2. And this one I'm going to get 1 divided by 3. Okay, so those are my coefficients. I feel like that's really too easy, but then if I want to plot my function, let's call it g of x. It's going to be equal to 1 plus x over 2 plus x squared over 2 plus x cubed over 3. No, that's not 3. That's 6. This is 3 factorial, which is 6. Sorry. Okay. So let's plot the function f of x equals e to the x and this function and see how they can compare. So I'm going to do that in Python. Let's switch over to Python, and then I'll come back and I'll do sine, and then I'll do another cool trick maybe. Let's just see where we go. Okay, so I'm switching to Python. Okay, so here I am in GlowScript v Python, and I really just want to make a graph. The first graph I want to make is of e to the x. So to make a graph in GlowScript v Python is actually quite easy. So I'm going to say g1 equals graph. I guess I should give it a title. X title is equal to x. Y title is equal to f of x. And then let's give it a width. Width equals 500. Height equals 250. Now I'm going to make two graphs. I'm going to make just f1 is going to be my actual function. G1 is just a name for the graph axis. It's not the actual graph. F1 is something I'm actually graphing. So it's a type of object called a G-curve. I'm going to give it a color blue. Color equals color dot blue. And let's do this. Let's give it a label. Label equals e to the x. And then F2 is G-curve. Color equals color dot red. And let's call this Taylor series. So now I need to pick my value of x. Let's just start with x equals 0, and then I need a step size. Because I'm actually going to calculate the value and just move to different point. Because this is, I need to pick that stuff. So let's say dx equals 0.01. I think this should be good enough. And then I'm going to say while x is less than, let's say, 2. So the first thing I'm going to do is to calculate e of x and plot that. So I can just do that all in one step. F1 dot plot x e hat x. There you go. Now let's calculate the value from the Taylor series. So let's just call this G Taylor. I don't know. And let's go here and say a0 equals 1. I could do this in a more complicated way, but I don't want to. A1 equals 1. A2 equals 1/2. A3 equals 1/6. I got that wrong over there. Okay. So this is going to be equal to, I guess I should do this. Let's just keep it this way. So it's going to be A0 plus A1 times x plus A2 times x squared. Oh my gosh, I just did that. I can't believe I did that. This is I think you have to do exp exponent x plus a3 times x cubed. And now let's plot that. F2 dot plot x G Taylor. And then increase the value of x. X equals x plus dx. Okay, I have a feeling that this is wrong, but let's just do it anyway. See, I knew I did something wrong. Punctuation line 5. That's not so bad. Oh, color.red label equals. Okay. That's pretty good. So you see up here from x equals 0 to, around 1, the two functions are very close in agreement. The further away you get, the more they diverge. I could add more and more terms, but if I'm just looking for something over here really close to the origin, my polynomial works fine. Okay, let's do sine, because that one's much more interesting. I'll do sine function. We'll do the Taylor series for the sine of x. let's even do, so let's first plot sine of x. I'm going to actually just delete all this stuff. So I have x, I have all that stuff. Let's get rid of that. And let's not calculate that. And let's not plot this. And then I'm just going to say sine of x. That's sine of x. And let's just see what that looks like. Okay, so I need to go further. So let's go x 6. I just picked a number. Let's go a little bit further. Let's go 9. Okay, that's good. So there's my sine of function. Let's expand this about a point of x equals 2. Yeah, let's do 2.66. So I'm going to go over to the paper and work on that, and then we'll plot that Taylor series too. So let's switch back over here to the paper. So 2.66. Okay, so I have f of x equals sine of x. And I want to expand about x0 is 2.66, just for the fun of it. Okay, so the first thing I need to do is to calculate my coefficients. So a0 is going to be f prime at x0 divided by 0 factorial. So let's just take my derivative. F prime of x is going to be equal to cosine x. So a0, I'm going to keep it over here. a0 is going to be cosine of 2.66. Okay, a1 is going to be the derivative of this, which is going to be negative cosine, negative sine x. So I get negative sine x. That's actually x0 over 1 factorial, so just 1. So a1 is going to be negative sine 2.66. a2 is going to be the derivative of f prime, which I didn't write. I'm not doing this in the right order. I should move these down. So f prime of x, x double prime of x, that's negative. Wait, where am I going? That's cosine. a0, why did I say cosine? Okay, f prime is cosine. Let's start, I'm starting over. I'm not focusing, that's what the problem is. Okay. Let's just go ahead and take all our derivatives. So I have f of x is sine of x. F of x equals sine of x. F prime of x is going to be equal to cosine of x. F double prime of x is negative sine of x. F triple prime of x is negative cosine of x. Okay, so a0 is going to be equal to sine of, this is called x0. a1 is going to be cosine of x0. a2 is going to be equal to negative sine of x0 over 2 factorial. And then a3 is going to be negative cosine of x0 over 6. And then my Fourier series, which I'm calling G, f of x is going to be equal to a0 plus a1 x minus x0 plus a2 x minus x0 squared plus a3 x minus x0 cubed. Okay, so now let's plot both. I've already got the sine function. Let's switch back over to Python and let's plot this. So I need to calculate my values. Let's first go x0 equals 2.66. a0, I'm just going to type in my values, so I can just type it out the long. Oh, I didn't switch. I'm sorry. There. So a0, I'm just typing in the equation I have over there is computer. a0 is a0 is sine of x0. No. Yes. A1 is cosine of x0. A2 is negative sine x0 divided by 2. A3 is equal to negative cosine x0 divided by 6. So down here, I can say G Taylor, like I had before, is going to be equal to A0 times plus A1 times X plus, X minus X0 plus A2 times X minus X0 squared plus A3 times X minus X0 cubed. And let's plot that. F2 dot plot X G Taylor. That looks pretty nice. I'm pretty happy. Okay, now you'll see here that I expanded about this point right here, 2.66, and they diverge when it gets further away, but it actually matches really closely up here. And this makes the whole graph kind of explode. Let's just fix that. So let's go up to 2.8. So if I go up here in my graph, I can say y max equals 2.88. There. That looks pretty nice. Okay. So you can see that in this region, they pretty much agree. But you can't get it to agree forever. I can't have a polynomial that repeats forever without having a repeating number of fractions. It would be kind of fun to build a function that automatically calculates. You can say n equals whatever, and it calculates it forever. But I'm just going to leave it like this. If you want this code, I'm going to save it. Let's save it right now. Save it as Taylor series example. And I will give you the code. It'll be linked down below. Okay, so I did say I was going to do a Taylor series trick, but I'll show you that in the next video, which I'll link down below also. That's it.